We've just looked at a few important properties of functions, or potential properties of functions, namely the idea of increasing or decreasing. And this was an interesting idea because it kind of highlighted a difference between global and local properties of functions. So a global property of something is something that's true about the entire thing. So for a function, it would be a statement that's true for everything in the domain. Whereas a local property is true when you are kind of restricting your attention to a small part of the domain potentially. So we saw an example where locally you might be increasing, so perhaps you're decreasing, maybe decreasing on an interval, but overall on the entire domain you are not decreasing. So it's kind of a subtle point. So what I want to do now is to look at two kind of broad properties which are very global in nature, so statements about the entire domain. So I'm going to start off with just some examples as always so that we have kind of pictures in our mind. So example. So I'm going to draw three graphs because these are going to be expressible most kind of immediately through their graphs. So let's take this, and we're going to have three copies of it. So what have I done? I've removed the X. Do I have enough room? Not quite. So let me just move these over. Just about. It's good enough. Okay, so let's think. I want to talk about what it means for a function to be bounded. So bounded means you are going to be somehow trapped within a certain region if you want. And there are three types of bounded we're going to think about. The first is the concept of being bounded below. So imagine if I took a graph and, I don't know, it looked something like this. Now, from what I've drawn at least, it's bounded below in the sense that there is a kind of a lower bound, if you want. So if I draw this horizontal line here, okay, dot, 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 and let's say the y coordinate here is A. So from what I can see at least, the graph is bounded below by this horizontal line. Now, we could also do something where it's bounded above in exactly the same way. Something like this. I'm just choosing a totally random graph. This is bounded above, isn't it, in a sense? Because if I draw this horizontal line, it never gets bigger than it. And we could have a scenario, and I suppose they kind of fall into this, where you are both bounded below and above. So you could have something like, I mean, I know it's very similar, but I'm assuming I don't get too big above or below. So let's imagine I could have something like this. So I could be bounded above by this line at B again, and we'll do it below as well at A. So maybe just to make this exactly the same, I should have it the same height, shouldn't I? Okay. So this is me basically drawing the graphs and observing that there are horizontal lines which the graph doesn't cross over at any point. And I'm assuming that's true in both directions infinitely on the entire domain. Okay, so let's make these a bit more precise. So definition. So I'm going to do this really, really precisely, just like I did with increasing and decreasing. Remember for those, we kind of drew a graph and I said informally, well, for increasing, f of x increases as x moves from left to right. I've done something kind of similar here. I've drawn some graphs and made some observations about certain properties they might have, namely they'd never cross these horizontal lines potentially. So let's really carefully think what this would mean. So the first one, so let me label this, let's call this one 1. So I want to describe 1 really precisely. So we're going to say that f is, so that's my function, is bounded below, if there exists a constant a just like I've drawn in this picture. Now what's the property? Well, if I was to take any position here, let's say there, so this would be comma x, open bracket x, comma f of x. So the f of x is the y coordinate. And we can see that the f of x has to be, well, greater than, in this way I've drawn it, strictly greater than the a. Okay, because it's above it on the y-axis, if you want to think about it like that. So let's do this really precisely. So if there exists an a such that a is strictly less than f of x. And now for the kind of the subtle point, I want this to be true for absolutely every x. Not just at one point, I want it to be true for every potential x. So that means every x in the domain. So for all x in the domain. So this is an example of a global property. It's an example of a global property because it's a statement about the entire graph, the entire function, all the information. You could make this local by saying it's bounded on some interval, which would be like saying, well, if I forget about the entire graph, but I only look at this part of the graph, for example. So if I restrict the domain to some closed interval, so, or open, it doesn't really matter, so maybe just from here to here. If you did that, then it's perfectly potential you could be bounded below, but it would be a local property because you'd have to say it was bounded below on some interval. Okay, so the concept of being bounded below, just full stop, is a global property. Okay, so this is me describing kind of precisely property 1, or the first picture if you want. But we can go through all of these and come up with basically exactly the same thing, can't we? So if I wanted to do the second one, so let's label that 2, shall we? Let's do it in a different color. Well, rather than write the whole thing out and kind of copy and paste it because it's virtually identical, there's only one major difference. Now instead of being bounded below, it would be bounded above. So we would say that f is bounded above. If there exists a constant, let's use the same notation as in the second picture, b, such that, well, f of x now is strictly less than b. You could have it less than or equal, it wouldn't make much difference. But again, this is for all x in the domain. Right, very important. Same up here. And finally, the third one. So can I actually move all this up so I've got enough room to fit it on one slide? Not quite. I tell you what I'll do. I'll just zoom out a little bit. So the third one, this guy bounded above and below simultaneously. I should say the other two pictures, they could be bounded below or above as well. It's just I'm only singling out that one property, right? So it's not completely clear. So it may be just to make sure we understand, I could be kind of going down, down, down like that here, or going up, up, up. So these first two pictures could be bounded above and below as well, but from the way I've drawn it, I'm only focusing on one of the concepts. So this guy, same basic story, but the last one, so I should maybe say this is 2. Let's be a bit careful, let's have enough space. So this middle one is 2. And now the last one, let's label it 3. So 3 over here. So we could say bounded above and below because it's both, but I'm just going to say it's bounded. So it's bounded if there exists, well, you need 2 constants now. So if there exists constants, A and B, such that, okay, well, it would have to be bounded above and below. So what would we have? In fact, I need to remove that. You'd be bounded below by the A, and you'd be bounded above by the B. Again, for all x in the domain. So this is an important definition. All right, this is a global definition from the way I've stated it because it is a statement about the entire domain. So let's make sure this is very highlighted. Okay, and maybe just to be extra safe, let's try and separate them a bit. Because it's kind of 3 different definitions, if you want, packed in. All incredibly similar, but different enough that we should label them differently. So first one, bounded below. That's the first picture. That means intuitively there is some horizontal line which you never cross underneath. Formally, it's a statement there is some number A such that A is strictly less than f of x for every single x in the domain. Bounded above, the same thing, but the inequality is reversed because you don't cross it above. And bounded, full stop, is where you have 2 numbers, a lower bound and an upper bound if you want. So maybe just to make sure the terminology is sensible. So I'm going to call this a lower bound when it exists. And I'm going to call this an upper bound. Right, so a nice way to view this, an important way to think about this, is in terms of absolute values, especially being bounded. So let's have a think about how to reinterpret the bounded property in terms of absolute values. So observation. So let's keep that there a second. Observation. So f is bounded. F is bounded if and only if. So this is an equivalent statement if you want. There exists some positive constant so I'm going to call it k, strictly greater than 0, such that, so here's a really slick way of giving you the bounded condition. The absolute value of f of x is strictly less than k for all x in the domain. Again, as always, for all x in the domain. We could have a restricted version where you're restricting to some interval, let's say, but the main thing here is this statement here. Now, why is this the same thing? Well, what's the absolute value? The absolute value is the distance from f of x to 0. So this is saying the distance from f of x to 0 is less than k. So this statement here, if you want to do it in terms of inequalities without absolute values, is exactly the statement that f of x has to be strictly less than k, but it has to be strictly bigger than minus k. Okay, that's what the meaning would have to be, right? Because you can't be on the left, you can't be to the left of minus k, because then you'd be greater than k distance away from 0. Same thing on the right. And so basically the k itself is an upper bound and minus k is a lower bound. If you were drawing a picture of this, which again you should always be able to do, or at least you should always kind of have a visual interpretation of a statement like this, so you can really kind of get your hands on why it's true. So what this is really saying is, if I was to draw these horizontal lines at k and at minus k, what this is saying is the graph is trapped between the two of them. It can't get out of that strip if you want. So visually, that's what it's talking about. Okay, so bounded, very, very important property, something that's going to turn up a huge amount as you delve into various aspects of calculus and functions and things like this. But it's important you understand what it means. And this is a really slick way of thinking about it. So this absolute value interpretation is only for bounded. If you want to do bounded above or below kind of separately, you just have the inequalities, right? So if bounded above is a statement like that, bounded below is a statement like that, the fact you can catch both is very nice. And I suppose the only other thing to say about this is, why do you know the upper and lower bound could be positive negative of each other? So how can I be sure that I can make them k on top and minus k on bottom? Well, the way to think about that is the following. If I take these two up here, this picture, okay, so you've got b up here and you've got a down here. Well, if I was to take minus b in this picture, if I was to take minus b, what would happen? You would have, I think b is further away from 0 than a, so minus b would kind of be down here. Okay, just in the way I've drawn the picture. So if you're bounded below by a, you're certainly bounded below by minus b, and then b would do the job that you're looking for. So that's the essential principle here, right? If you had an upper and lower bound and they weren't plus and negative of each other, you would choose the one with the largest absolute value, and that would be your k. It would work. So kind of neat. So there we go. It's the concept of bounded. Very important. Not every function is going to be bounded. Some are most definitely going to be unbounded. But determining if functions are bounded is super important.